Hi, I'm Dr. Courtney with the Quantitative Reasoning Center. After you finished the assigned homework for Calculus 3, I bet you feel like you've had a real workout. Well, the math class is the weight room for the mind. A strong, disciplined, and well-trained mind is important for officers in the modern Air Force. Today we're having a look at section 12.5, number 18, and number 60. Let's start with number 18, which asks us to find parametric equations for the line segment, and take care because I'm changing the numbers a little bit so you still get the benefit of solving these at home. So we have 2 points. Let's call one 5, 3, and 1. And let's call the other one 10, 6, and -3. And let's go ahead and have a careful problem-solving framework to use. So the big idea is to use the displacement vector to find the parametric equation of the line segment. It's told there'd be no spelling. I was thinking Arby's. Between the 2 points. Alright, and to develop this, in other words, we need to make our plan. So here's sort of P1 and here's P2, and we want the line segment between the 2 points. So we can think of this as x1, y1, z1, and this point we'll call x2, y2, z2, and these are just 2 Cartesian points in 3-dimensional space. So one thing we want to do in our plan is we want to compute the displacement vector between the points. And let's just suppose that our displacement vector, if we end up with D is equal to something like A, B, C, and then we can write down our parametric equations rather directly. X would be x1 plus AT, y would be y1 plus BT, and z would be z1 plus CT. And now we need to consider our domain of t, and t is going to go from 0 to 1. And the reason that this approach works for determining the parametric equation of a line segment between 2 points is because at t equals 0, you end up at P1, x1, y1, and z1. And at t equals 1, you end up at that point plus the displacement vector between the 2 points, which puts you at the second point. Alright, so that's the development. Now, to evaluate, let's go ahead and compute this displacement vector. D is going to be, well, the vector, and this is P1 and this is P2, so it's 10, 6, -3 minus 5, 3, 1. So 10 minus 5 is 5. 6 minus 3 is 3, and -3 minus 1 is -4. So now we can identify A, B, and C, and we can finish evaluating. X of t is going to be x1, which was 5, plus A, which is 5, times t. y of t is going to be y1, which is 3, plus b, which is 3, times t. And then z of t is going to be z1, which is 1, plus c, which is -4, times t. Alright, so these are equations, parametric equations for that line segment, and we need to note that t goes from 0 to 1. And now let's zoom out for a minute and think about how we would assess to double check and make sure that our answer is correct. So to assess, let's plug in t equals 0 and t equals 1, and this should yield P1 and P2. So for t equals 0, x of 0 is simply equal to 5, y of 0 is simply equal to 3, and z at t equals 0 is simply equal to 1. So we got our starting point back. Now we can double check at t equals 1. Well, at t equals 1, x equals 5 plus 5, or 10. Y is 3 plus 3, or 6. And z is 1 minus 4, or -3. And indeed we do get our second point back, 10, 6, -3. So our assessment shows that our solution is correct. Alright, number 60 asks us to find the equation of a plane for all the points that are equidistant, and then we're given 2 points at that plane. All the points in that plane are equidistant from these other 2 points. So the big idea here is we want to use the distance formula to represent the given information as an equation. Alright, now we need to develop this idea. Well, good idea to draw a picture here. Here's P1 and here's P2, and we're kind of thinking about the plane that's equidistant in between them. And the idea here is that if we had an arbitrary point in space, call it x, y, z, then this distance, we'll call it d1. In other words, we're letting d1 be the distance from point P1 to our point x, y, z, our unknown point. And let's call this d2. So our two distances are d1 and d2. So our plan is to develop, well, let's not say develop. Why don't we say express d1 and d2 in terms of x, y, z, and the given points. And the next thing we can do is we can set d1 equal to d2, because that's kind of our given information. In other words, that's what equidistant means. Equidistant means that the two distances are equal, and then we can square both sides, and then we can simplify. Alright, now as we evaluate our plan, I'm not going to solve the whole problem because I didn't change the numbers from the book. I'm going to kind of get you started, show you how it goes, and then leave it up to you to exercise the plans and the steps in the plan that we don't quite get to, as well as assess and consider whether or not the answer you found makes sense. Alright, so to evaluate the problem, well, the distance formula, d1, is equal to the square root of x minus 2 squared plus y minus 5 squared plus y minus, oops, that should be a z. Z minus 5 squared. In other words, this is the x-coordinate, the y-coordinate, and the z-coordinate, so this is d1. d2 is analogous. The square root of x, well, x minus negative 6 is x plus 6. Y minus 3 squared plus z minus 1 squared. Alright, so I'm going to go ahead and do a bit this in my head. Set them equal and square both sides. You get x minus 2 squared plus y minus 5 squared plus z minus 5 squared is going to be equal to x plus 6 squared plus y minus 3 squared plus z minus 1 squared. And this is the point where I'm going to sort of show you some things that are going to happen and talk about it, and then leave the rest up to you to solve on your own. When you FOIL out all of these binomials squared, you're going to have an x squared, a y squared, and a z squared term on the left-hand side of the equation. And you're also going to have an x squared, a y squared, and a z squared term on the right side of the equation. And since the coefficient of all the squared terms is 1, the x squared on the left is going to cancel out with the x squared on the right, and likewise for the y squared and the z squared terms. So you're only going to be left with linear terms in x, y, and z, plus you have to gather all the constants up and you'll have a constant term. Well, what do you have if you have a constant times x plus a constant times y plus a constant times z is equal to a constant? Well, that's the equation of the plane, and following it through in the way I just described would complete the solution to this problem.